Hello, I'm Yingfei Zhang from Peking University. I'm presenting on behalf of Zhentao Ye, who is unable to attend POPL'26 in person due to visa issues. This talk covers the paper, Accelerating Syntax-Guided Program Synthesis by Optimizing Domain-Specific Languages, which is a joint work between Zhentao, Ruyi, Yingfei, and Xiong, all from Peking University. Modern program synthesis, especially syntax-guided synthesis, rests on two pillars: semantic constraints, which specify what the program should do, for example, input-output examples or logic specifications, and syntactic constraints, which restrict how it may be written, typically encoded as a domain-specific language DSL. This work focused precisely on that syntactic constraint, the DSL. Studies have shown that the choice of DSLs may significantly affect the efficiency of synthesizers. It follows a Goldilocks principle. Too general, the search space explodes. Too constraints, the task becomes unrealizable. Finding the sweet spot typically requires manual tuning by experts. Our goal is to automate this process. This work studies how to ultimately refine a DSL to accelerate synthesis on a target domain. The framework starts from a representative task set and iteratively modifies the DSL to reduce average synthesis time. But evaluating each candidate DSL by running the full synthesizer across all tasks is prohibitively expensive. So the key challenge is efficient DSL quality estimation without invoking the synthesizer. The solution is to estimate synthesis time using the enumeration ranks of feature components. Program fragments in solution programs whose positions in the grammar directly govern search space structure and correlate strongly with actual solver performance. Let me illustrate the goal of this work with a concrete example. Consider a single string manipulation task from Sega's comp. Given an input string that may contain an ID and metadata separated by a pipe, extract the substring before the first pipe. For example, TL-18273982 pipe 10M should yield TL-18273982. If no pipe is present, return the input unchanged. Let's solve this task using EUsolver, a widely used synthesizer. EUsolver works by enumerating small program fragments and composing them via decision tree learning. We start with a standard manually designed DSL, call it L0. It includes some basic atomic operators, such as concat, substring, index of, and if-then-else. Under L0, EUsolver finds the solution P1. ITE contains X pipe, substring X0, index of X, pipe 0X. Now imagine a refined DSL L1. In L1, we introduce two operators, F1 and F2, which are macros for substring and index of, respectively. The raw substring and the index of and some other operators are removed. The solution simplifies to ITE contains X pipe, F1X, F2X, and X. Switching from L0 to L1 yields a 6.11 times speed up on this task, demonstrating how target DSL refinement directly accelerates synthesis. So the goal is to automatically discover L1. A natural approach is a search loop. Generate a candidate DSL, run the synthesizer on the task site, and measure speed up. But invoking the synthesizer is prohibitively slow. For instance, evaluating thousands of DSLs in the bit vector domain would take years. Hence, the central question is, how can we estimate synthesis time for a given task without running the synthesizer at all? Our key insight comes from observing how a naive enumerative synthesizer behaves. First, consider how to estimate its synthesis time. Such a synthesizer enumerates programs in order of increasing AST size, that is, by the number of grammar nodes, and check each candidate against the semantic specification. For example, input-output examples, until it finds a correct solution. Since checking a candidate program is roughly constant time across candidates, the enumeration rank, the position of the solution in this ordered sequence, serves as a faithful proxy for synthesis time. This rank-based estimation is designed for naive enumerative synthesis. But how do we extend it to solvers like EUsolver? The key insight is EUsolver constructs solutions by composing program fragments, and those fragments are generated by a model similar to a naive enumerator. Crucially, EUsolver can only assemble the final solution after all required fragments have been enumerated. So the total synthesis time is strongly correlated with the time needed to enumerate the largest fragment used in the solution. We call this fragment the feature component. In our example, the fragments EUsolver needs are underlined, and the feature component is substring x0, index of x, pipe 0. Since EUsolver enumerates fragments by increasing AST size, we define the feature component rank as its position in that enumeration sequence. Computing this, we find the synthesizer must enumerate 3,158 programs before generating this fragment, so its rank is 3,158. We discovered that the feature component rank acts as a key predictor of synthesis time cost. This allows us to quickly estimate the synthesis time, and thus the effectiveness of a candidate DSL without actually running the synthesizer. If we know the solution program, we can simply calculate the rank of its feature component under a new DSL. This calculation is nearly instantaneous. By estimating the performance of the new DSL on each synthesis task based on the feature component ranks, we avoid the huge overhead of directly calling the synthesizer, thus making the cost of the automated search process acceptable. Now, let's revisit EUsolver's behavior under the optimized DSL L1 from the feature component rank perspective. As before, we underline all fragments generated by the enumerator and identify the feature component as F1x, F2x. Its rank is 58. So the enumerator now needs to generate only 58 programs, down from 3,158, yielding a 6.11 times speedup. The sublinear speedup, that is 3,158 divided by 58, is approximately 54.4, but observed speedup is only 6.11. A reason because EUsolver's enumerator employs optimizations, such as observation equivalence, beyond naive enumeration. Synthesis time overheads, for example, decision tree learning, also contribute. In short, the feature component rank is a key predictor of synthesis time, and optimizing it drives measurable acceleration. We have shown that feature component rank predicts synthesis time for EUsolver. Do other synthesizers admit a similar notion? We analyzed state-of-the-art tools across Saiga's benchmark domains: DryadSynth on bit vector domain, Duet on string domain, and Polygen on CLIA domain. Though their algorithms differ significantly, we find that every solution can be decomposed into enumeration-derived fragments, and the largest such fragment is consistently the feature component. This universality lets us generalize our method beyond EUsolver. For example, the underlined parts in these solution programs, generated by each respective synthesizer, are precisely those enumeration-derived fragments. Based on the feature component's rank, we propose AMaze, an automated DSL optimization framework with 3 phases. Preparation: run the synthesizer once on the training set using the initial DSL, and collected all solution programs. Mining: extract frequent syntactic patterns from those solutions to propose additions. For example, macros like F1 and F2. Search: use a genetic algorithm to explore the DSL space, guided by feature component rank estimation, not actual synthesis. The core technical challenge is how to compute feature component ranks efficiently. First, for a new DSL, how do we obtain a candidate solution program without invoking the synthesizer? Second, even if we had the solution, enumerating up to its rank is intractable, as program count grows exponentially with size. For the first problem, we use rewriting. Giving a solution under the original DSL, we rewrite it into the new DSL using macro definitions, for example, F1 and F2. Since modified DSLs are conservative extensions, this rewrite is always possible. For example, substring x0, index of x, pipe 0, becomes f1x, f2x. When the rewritten program remains structurally similar to the true solution, its feature component rank serves as a tight upper bound on the actual synthesis cost. We periodically update this solution set by running the synthesizer to collect new solutions, refining our approximation. For the second problem, we design a dynamic programming algorithm that computes the rank of any program in time polynomial in its AST size, supporting both AST-based and term graph-based enumeration orders. We implemented AMaze and applied it to optimize DSLs for state-of-the-art synthesizers through cross-validation. Our evaluation uses benchmarks from SciGasConf 2019. 750-bit vector synthesis problems from the BV track for evaluating DryadSynth, 209 string synthesis problems from the SLIA track for evaluating Duet, 100 CLIA problems, 82 from the general track, plus 18 solvable by Polygen for evaluating Polygen, and all 1,059 problems combined for evaluating the general purpose synthesizer EUsolver. Our research questions are: can AMaze accelerate state-of-the-art synthesizers across domains by optimizing DSLs? How does AMaze compare to existing DSL modification methods, which optimize for expressiveness or conciseness, not synthesis speed? Application study: what is the individual contribution of each core technique in AMaze using feature components, and using enumeration ranks to end-to-end acceleration, thus removing either degrade performance significantly? The results show that AMaze consistently accelerates state-of-the-art synthesizers across domains. On DryadSynth, we achieved a 1.09 times speedup. On Duet, we achieved a 3.62 times speedup. On Polygen, we achieved a 1.53 times speedup and solved 3 more tasks. On the general purpose solver EUsolver, AMaze achieved a 4.35 times speedup on average and solve 129 more tasks. As a baseline, we implemented a modified version of AMaze that simulates Stitch, a library-based synthesis approach, by minimizing the overall program size across a given set of solutions. Under the same setup, it achieves modest speedups on some synthesizers, but causes severe slowdowns on others, demonstrating that size minimization alone is not broadly acceptable and can harm performance for certain solvers. Finally, we conducted an application study to isolate the impact of AMaze to two core techniques: estimating synthesis cost using feature components instead of full programs, and using enumeration ranks instead of program sets. The results shows that both contribute significantly. Using feature components alone yields moderate speedups, though worse than full AMaze. Using enumeration ranks alone, however, leads to slowdowns on average. To summarize, we present a framework that transforms DSLs design from a manual art into an automated science. By leveraging feature components and efficient enumeration rank estimation, it automatically tailors DSLs to specific domains, significantly accelerating modern synthesizers. And thank you for attention. Zhentao is currently exploring opportunities in industry. Feel free to contact with him after the talk. If you have any question about the paper, please contact the authors directly. Thank you.